Hello. What you're seeing on your screen is a code for an adversarial search game. It's a super exciting game. I'll shortly show you the demo. But before I show you the demo of MiniMax, let me make you comfortable with the code that you're seeing. So we just import NumPy, which is a library for number processing, and some features of math will be used. So we import from Math Infinity. This is a two-dimensional array, and this will be the game state. What is the game state? Now, if you recall, in tic-tac-toe, there are 9 spaces on a 3 by 3, on a 3 column, 3 row grid, and this is where we are creating it. Then, if you can recall from your tic-tac-toe experience, there are 2 players, one is X and one is a 0. So they take one by one, they take their turn and they put a 0 or a cross to make sure that they are able to win before their opponent. The rules of winning is either you have a hat trick on the horizontal, or you have a hat trick on the vertical, or you have a hat trick on the diagonal. Having shown you the setup of board, let's see how it is run and what it does. So I would like AI to go first. Now, I did not do anything. The AI put its mark on the second spot of 9 grid. And now as a human, I'll choose my own space. Now just see, if I type in 2, 2 is already occupied. So it will not put a cross over there. It will say block is not empty. You blockhead, choose again. So I choose say 5. Now it has put a 5, my 5 over here, and then the AI has played its move. So I'm not letting the AI do a hat trick, and now I'll put it here and I won. Right? I don't want to try again. I just want you to see that I won because the diagonal hat trick was checked true and I was playing with the AI. Now we will see how this game was played through Minimax, what is Minimax, and what is the use of this kind of search logic. Minimax is an algorithm for adversarial games. Adversarial games or adversary search is a case when we know that we will have turns to make ourselves most profitable or in the most successful position. And then the other turn will be of our opponent who will try to reduce our chances of winning or getting the maximum benefit. However, when it will be our turn again, we will again try to maximize our side of utility, and this will keep on happening in reverse. So from my point of view, when I'm trying to maximize, which is my chances of winning, the adversary in the case that I just shown, the AI logic was trying to minimize the same thing. And then on the next turn, whatever had been done by my adversary and whichever way the game changed because of that, I took that state and tried maximizing it again. This approach is called a mini-max approach because one player on one turn is minimizing the possibility of one's perspective, and on the other turn, the same possibility is being maximized. So if we look at a two-ply games tree, let's say that we're just looking at 3 levels of depth, and at every level there are 3 possibilities. And for every possibility, there is a certain cost or a certain utility or a certain function value. So moving to this possibility is 3, this is a 2 score, and this is a 2 score. At each possibility, there are 3 more possibilities with their respective scores. We know that the first turn will be that of a maximizer. It can start with a minimizer too, but because it says maximizer, we know that this is the turn when the perspective is being maximized. And this is the turn of the opponent. So he or she is trying to, or the AI algorithm is trying to minimize the chances of scoring high. And then on the next turns, we will maximize again. However, the way this game should be seen is that when you are playing tic-tac-toe, you think if I take this, if I if I if I uh, if I take this step, what step can the opponent take? This, or this? And when they will take this step, what steps can I take? I can take all these steps. So we don't go very deep into thinking of steps in future, but at least whenever we're playing a game like chess or tic-tac-toe or ludo, we go 2 to 3 steps ahead in our prediction and see, okay, if I move like this, these are the choices for my adversary to move in, and when adversary will pick one of those choices, these are the choices that I will have. So this is the numerical or the tree form of the same decision making. So we start from bottom up to decide what will be the value here. We know that the possible values at this level are the following. If the minimizer has taken us here, we'll have a, a choice to make which will give us a 3 credit or a 12 score or an 8 score. Um, because we were maximizers over here, we had picked up the maximum scores that were available. Similarly, over here, we had picked up maximum from the level below this. Now, at this level, maximizer has maximized its chances of scoring high. This is the turn of minimizer. Whatever the choices are here, we know that the minimizer will pick the smallest one. So from this pool, it will pick up 3 because 3 is smallest of the choices. From this pool, it will take a step or play the game position, be on the game position where the score is the lowest. So it will be 2. And from this pool, it will be 2. So the minimizer has given the options of going here and getting 3 score, or here and getting a 2 score, or here or getting a 2 score. Now minimizer's turn is over, and now it's again maximizer's turn. But by now the maximizer is left with this state to maximize on, and it picks up the most profitable score, which is 3, and chooses to go in this direction. This is called a mini-max algorithm. One way to look at the tic-tac-toe in a mini-max perspective is on the screen visually. Now, mathematically, you can think of this game as maximizing what has been minimized of all the possible options in the past. Which actually means that when it is the maximum stance, you will maximize on this turn whatever was minimized in the previous turn or the successors. So the max value is that if we are still not in the terminal state, then we will try to attain a maximum score of all the options that are there, all the vertices that we can go to reach the minimum values of our previous turn, which was our adversary's turn. For the minimum value, instead of maximizing, we actually do minimizing. We know that this max comes turn by turn, and there's a turn for max and then turn for min. So first turn, maximization of the previous minimization is being done, and then on the next turn, minimization of what we know has